Welcome to the virtual presentation of MorphingCircuit, an integrated design, simulation, and fabrication workflow for self-morphing electronics. Recently, we have seen a boom of non-planar surfaces equipped with functional electronics, which enable sensing and display directly on the surface of a product. However, manufacturing such non-planar electronics often requires specialized manufacturing processes and materials. Furthermore, most of the existing techniques are incompatible with complex geometries. What if we utilize the material's ability of shape transformation, such that a circuit can be manufactured in a planar version and then transformed to a complex 3D structure? In response, we introduce MorphingCircuit, an integrated design, simulation, and fabrication workflow that combines electronic functions with forms, which efficiently reduces cost, production time, and e-waste. MorphingCircuit has its unique advantages over existing circuit fabrication techniques. Particularly, it is a self-morphing technique for manufacturing circuits with complex curvilinear surfaces. Here, the morphing occurs during the manufacturing process. A flat sheet can self-morph into 3D complex geometry. Then, how to achieve the self-morphing electronics? Actually, our group has been working on self-morphing interfaces for a while. For example, we developed a series of 4D printing techniques to achieve origami self-morphing structure, reversible self-morphing structure, mesh topology-based large-scale structure, linear self-morphing structure for compliance mechanism, double curvature structure for continuous surfaces, 3D self-morphing structure for shrinkable adaptations. Accordingly, we aimed to integrate self-morphing techniques with electronics. Due to the integration of conductive traces, morphing a circuit is not as easy as we thought. For example, we took 3 basic morphing mechanisms as our mechanism verification test samples, which are twisting, bending, and coiling, respectively. The top row pictures are pieces without traces. The bottom row pictures are pieces with traces. All the traces significantly affect the morphing preference. To mitigate the effect of the traces and optimize the trace placement, we developed a simulation tool based on FEA method and the residual stress releasing computational model. The blue color represents the minimum stress area, which is also called the golden area. Since the area is with the smallest value of stress, it is recommended to align and print with a silver trace. That means if we print the traces on the golden area, it should be the least influenced. The experimental results show that with traces printed on the golden area, the transformation is much less influenced than those with traces printed on the non-golden area. Then, we integrated the simulation tool in design and fabrication process to achieve MorphingCircuit. Take the 3-leg robot as an example. Users start by creating a profile of a 2D substrate and assign an actuator type for each chosen block. Then, the simulation platform helps to predict the transformation and suggest preferable areas where the traces can be applied. Utilizing the simulation result, the next step is to design PCB schematics. For the fabrication process, we applied conductive traces with a standard screen printing process, and we suggest using a spacer to lift up the side for double side traces. We designed sinks on the substrate for electronic components to settle in. After assembly, we applied extra silver ink to the connection points. Then, we put the whole piece in the oven for triggering and silver ink curing. This is a light-chasing robot with integrated surface mount photobodies, transistors, vibration motors, and a battery. When light is shining, the robot will move to the path of light. We can also design an interactive and portable product, like this Christmas tree with touch sensing and hover sensing. When the user first touches the tree near the silver traces, all LEDs turn on. Then we can use hover motion to control its brightness. As you can image, this kind of shape with electronics is hard to achieve with conventional 3D printing, like injection molding or vacuum forming technique. Here is another interesting application area. We can utilize the morphing structure to prototype tunable electronic components such as capacitor, resistor, inductor, and switch. Each component can be printed with a custom shape and desired value range. This is a conductor. We can tune its value by designing different size of spring. This is a switch. By locking the edges to different positions, different colors of LEDs are lighting up. This is a capacitor. We can tune the value by controlling the distance of the two panels. Beyond screen printing silver traces, we can coat the conductive layer using a standard sputter coater. This is the transforming process in hot water. We use this structure as a capacitive humidity sensor. After treating, we put 2 of them in the soil. It shows that when the user pours water to their plants, 2 visualized bars are shown. Last, we envision these morphing circuit applications can extend the boundary of our galaxy of self-morphing technologies and incite a search for even larger design spaces of self-morphing interfaces. Thank you.